All right, here we go. So let's take a look at our lesson for today. The functions that we're going to be looking at, and let's put some different words with them. They're calling A the constant function. We would call this a horizontal line. And they are horizontal line. And they're calling B the identity function, f of x equals x. This is just the parent line. This is just a line. Absolute value function, hopefully I'm sure we recognize it's got the little straight, like the straight lines on either side of the x, absolute value x. We've got the square root function. This is the parent, the square root of x. We've got the parabola, x squared, and the cubic function, x cubed. This, they're calling the reciprocal function. We typically refer to this as a rational function. This is a rational function. And the last one is kind of the new one. We haven't really talked really any about the greatest integer function. The greatest integer function is also called a step function because, I mean, it looks like stair steps, right? That's what it kind of looks like. And so some textbooks will call this the step function. This is called the greatest integer function. This notation that we're seeing right here with the, right there with like, it looks like a double bracket. Apparently our textbook likes double brackets. I usually use just a bracket. So what's going to be important for us is to make sure we're looking at the difference that this would represent the greatest integer function, and this with the straight lines would represent absolute value. So it would be important for us not to get those two confused because they're quite different. So let's spend a little bit more time talking about the greatest integer function. Let's just talk about some, because we really haven't looked at it before. To calculate values, so it's y values, to calculate y values of the greatest integer function, you would choose the integer to the left or the smaller one. Now that probably doesn't make any sense right now, so I'm going to do some examples of what that means. So let's kind of go back to what we know. If we were looking at absolute value, we know that if we did the absolute value of, say, -5, we know what the absolute value function does, right? It turns negative numbers into positive numbers. So if we did the absolute value of -5, we would get 5. That's just something that we are familiar with. So that function does something to the numbers. Well, the greatest integer function also does something to the numbers, but what it does is a bit weird. It's kind of strange. So for an example, let's just do an example. Let's say we were doing the greatest integer of 2.1. Okay, so I'm going to show this with like a number line. So we've got 0, 1, and 2. Whoops. We'll do 1, 2, and 3. I'm going backwards. 1, 2, and 3. Okay. So 2.1 would be like, like right here, right? That's where 2.1 would be. What we do is we go backwards, we go left to the closest integer. So the greatest integer function gives you an integer. That's what it does. An integer, if you recall, is a whole number. It gives you a whole number. So if I wanted the greatest integer function of 2.1, that would give me a 2. That would be the value that the greatest integer function would, that would be the output. That's what you would get if you did the greatest integer function of 2.1. All right, let's do an example with negative numbers. So let's say we wanted to do the greatest integer of negative 4.3. Okay, so we do our little number line. So we've got like negative 4, negative 3, negative 5. So negative 4.3 would be, I don't know, around right here. Now we got to keep in mind we want to go left. Our integer that's going to be the result of our work is the integer to the left. So the greatest integer of negative 4.3 would be negative 5. So I just really need us to understand how those little brackets work. What happens? How does it work? Okay, are we okay with that? Is everybody okay? So that's what it does. I know it's kind of weird. It's pretty weird, but that's what it does. And it creates little stair steps is what it does in the graph. The graph is like little stair steps. All right. So that's the functions we're going to be looking at. Let's get a reminder of our transformations that we worked on last year. So the transformations that we worked on last year, just to remind you, for adding and subtracting, that's this top row. For adding and subtracting, if you're adding and subtracting inside with the x, it has the opposite effect. If you subtract a number, that shifts it right and changes the x value. If you add a number, that shifts it left and also changes the x value. So that's just a reminder. If you're adding and subtracting and it's not inside with the x, if you're just adding to the y values, that would shift it up and change your y value. This would shift down again and change the y value. So that's a reminder. That's just a reminder about adding and subtracting. Let's look at multiplying. So if we were to multiply, this one is like the negative, like negative 1 is outside, then what that does is it reflects the graph over the x-axis and changes the y value. If the negative is inside with the x, it reflects over the y-axis and changes the x value. Okay, and if it's just a plain old number, if the plain old number is outside, it's a vertical stretch and it changes the y value. If the number is inside, it stretches horizontally and changes the x value. So those are reminders. And, you know, the transformations might be helpful when we're graphing. It might kind of help you know what should your graph be looking like. I mean, what kind of transformation do you see from the parent? All right, and so that's just a reminder for us. Any questions about that? Okay. So what I want to do next is look at piecewise functions. So piecewise functions we did look at last year. Some of us had a little bit of trouble with piecewise functions last year, so they're very important, so let's just look at them again. And let's recall what's going on. What's going on is these x values are the assigned domain of each piece. Those are the domains for each of the pieces. Okay, so if we look at the top one, the top piece, its assigned domain is x is less than or equal to -1. So if I'm looking up here on my graph of that -1/3 x plus 4 squared plus 2, that function should be graphed only where x is less than or equal to -1. It should not be graphed anywhere else, nowhere else. Really important. And that's one of the things that we had a little bit of trouble with last year, is sticking to just the assigned domain. Okay? The middle piece's domain starts at -1 and goes to 4. So I would start at -1 and I would go to 4. And that's where that absolute value graph should be. It shouldn't be anywhere else, just between -1 and 4. The last piece is this where x is greater than or equal to 4. That cubic should be here. It should be from 4 and larger, that cubic function. That's where it resides, nowhere else. So let's look at a difference between like the solid points and the points that are open. Okay, let's take this solid point for instance right here. This solid point is solid because that's greater than or equal to. Remember, if it has the extra little line underneath it, it means or equal to, and that's going to give us a solid point. Okay, let's look at an example of a point that is like open. This is an open point. Okay, let's look at this one. This one is an open point. And the reason this one is open at -1 is because that is just a less than. -1 is less than x, not or equal to. So does that bring back some memories about the whole solid points and open points? Okay, let's just make ourselves a little note out to the side. So if it's less than or equal to or greater than or equal to, that's going to give us a solid point. And the points I'm talking about are the ones at the breaks, like at -1. Not the ones inside here. The ones inside here are going to be solid, right? The ones inside here are solid. The only one that has a chance of being solid or open is the ending point of the domain, the end. Now, if it's just less than or greater than, then we're looking at an open point. And that's a little bit of a review on piecewise functions. Any questions on piecewise functions? Okay. So let's go to, we have a couple of examples on the next slide where we're going to graph the greatest integer function and we're going to graph a piecewise function. The greatest integer function is, I'm just going to be perfectly honest, it's one that, you could probably tell, it drives some students crazy, right? It's a little weird. It's weird. Okay, so the greatest integer of 2x plus 1. So let's think about, before we graph, it might be helpful to think about the transformations. Okay, so this 2, if we think about what that 2 does, if we go back, let's look at our transformations. It's inside with the x, it's this right here. It's inside with the x, it's going to affect the x value. It actually has the opposite effect. When the number, let's just make ourselves a note here, when the number is inside with the x, it has the opposite effect of how it appears. For example, f of x minus 2 means right 2, not left 2, right? That means right 2. It seems like it should be left 2 because it's minus 2, but it has the opposite. It's opposite. Likewise, if I have f of 2x, it looks like I'm multiplying x by 2. That's what it looks like, but I'm actually dividing x by 2. So it has, when it's inside, it has the opposite effect. That's just a review. We talked about that last year, just to hopefully spark that memory. Okay, so when we look at the greatest integer function here with the 2 inside of it, we should expect 2 to be half as long. So we should expect, the x should be half as long. And this transformation says it's going to be shifted up 1 from the parent. So let's look at what the greatest integer function looks like. Let's look at that graph one more time. Each of those little steps is 1 unit long. Do you see where it is? So, like for example, this one starts at 0 and it goes all the way to 1 with a hollow place at 1. It's 1 unit long. Every step is the same length long. They're 1 unit long. So if it's just a plain old x for the greatest integer function, your step should be 1 unit long. Okay? And where one of these ends, like see how there's a hole there? The next one begins with a solid one. Right? That's how the greatest integer function works. When one ends with a hole, the next step starts with solid. And then it ends with a hole, and then it starts at the next step up with solid. These are like steps, which is why some textbooks call this the step function instead of the greatest integer function, like stair steps. All right, so now let's work on our graph. What I like to do is I like to do a table, a T-chart. That's how I like to do it. I mean, there's lots of different ways. You could try to transform it from the parent if you want to memorize the parent. I don't really want to memorize the parent, so I just plot points. And what I like to start with is what, with any graphs that I like to start with, I like to start with -1, 0, and 1. That's what I like to do. So that's what let's do. Let's start with -1, 0, and 1. So I'm going to, on the y side, I'm going to show the work. You don't have to show the work. I want to make sure that we know what's going on. So I've got the 2. I'm going to put in a -1 where the x is. All right, so I've got the greatest integer of -2, which is -2. So if an integer goes into that little greatest integer function thing, an integer comes out, then really nothing happens to it. So that's going to give me -2 plus 1, which is what? -2 plus 1, -2 plus 1, which is -1. So -1, -1. There's a solid point right there. Okay, great. Now let's try -1, 1. Where am I? -1, so -2 plus 1 is -1. On the other side. Oh, yeah, -1. Thank you. -1, -1. Perfect. -1, -1. Okay. So now let's plug in a 0. So 2 times 0 plus 1. So let's see. 2 times 0 is 0. So 0 plus 1 is 1. All right. So 0, we're at 1. Okay, that already looks weird, doesn't it? They're like 2 spaces apart from the y, like the y goes up 2. So there's something weird about that. let's put a 1 in. 2 times 1 plus 1. So that's 2 plus 1 or 3. So 1 would be at 3. Okay, so those are definitely solid points, but I still don't have enough information to graph. So this is like a work in progress. You just have to figure out which numbers you want to use. You know, we had the clue that x is supposed to be like half as long. So instead of being 1 unit long, it's probably a half unit long. So why don't we check out and see what happens when x is 1/2? Let's just check that out. So again, this is not an exact science. We're just working, we're putting points in so we can get a better idea of what happens to the graph. So it's just flexible. If you want to know what's happening at a particular location, put that point in. So I put a half in, and I've got 2 times a half plus 1. Let's see, 2 times a half is 1, and 1 plus 1 is 2. So at a half, I'm at 2. Oh yeah, that makes sense, because these are like half length of the others. That's what we kind of anticipated by the transformation, the way that we think about transformations. If I'm concerned and I don't think I'm doing it right, I could try what happens at negative 1/2. So 2 times negative 1/2 plus 1 would be what? Negative 1. Negative 1 plus 1, or 0. And that's what we would expect. We would expect negative 1/2 to be at 0.
So whenever you're doing the greatest integer function, like with the brackets, is the reason why it's just going to be the same is because it's not like a decimal, right?
Exactly.
So
it's
you're
not
having to like pull out like the number line.
Exactly. Exactly. These I was actually, okay, so I like doing the integers. It's easier, right? So I was working with integers first, but I do want to investigate what happens when it turns into a fraction. I do want to do one more. So you're right. When an integer is inside the integer function, it doesn't do anything to it at all. It just results in the same thing you have. So just to make sure we're thinking correctly, what I would like to do is, here's what I'm thinking. Okay, here's what I'm thinking. I'm thinking that this graph is going to look like this. It's going to go out and it's going to go to where that is. It's going to, those little steps are going to be like half a unit long instead of a full unit long. But to verify that I'm thinking correctly, why don't we put in, say, I don't know, 1/10. Let's like put in 1/10 and see what happens. So 1/10 would be 2 times 1/10 plus 1. So the greatest integer of, let's see, 2/10 is 1/5 plus 1. So let's think about this on our number line. 1/5 is probably about right there. And I'm going to go left. Right? That's what we do. We go left. So that's going to give me 0 plus 1, which is 1. So at 1/10, which would be, you know, like, I don't know, around right here, 1/10 is 1, which is what we anticipated. It's working correctly. So I'm going to pause here for a second. One thing that we were a little bit confused with in the last class is like the extending this piece. So when this, let's look at this piece right here. When it comes, so it starts here at 1 and then it goes to like 1.5 and there's a hole. What that means is you're going to start the next one directly above it with a solid and then move to a hole. And then once you know the pattern, there's no reason for you to have to do a bunch more points. Just complete the pattern. Your graph should be completely filled, right? You should fill it. So I need some down here. So I've got this one, which I'm going to, you know, it's got a half space. this one. So let's just keep populating the graph. Just follow the pattern that we discovered through points. We discovered what the pattern would be. That's the reason that you plot the points, is so you can discover what the pattern is. Once you have the pattern, then you just go with the pattern. If you're not sure you're doing it right, you should check another point. Okay, so a couple things about the greatest integer function. Let's just write some notes. Okay, so one note is when one step ends, the next one begins directly above it. Okay, when one step ends, the next step begins directly above it. And the other note we need to make is we need to fill out the graph. Okay, it needs to be completely full. We shouldn't have any more room to draw one of those little steps. They should all be filled in. So your steps should start at the bottom of the graph and go all the way to the top. All right, any questions? Okay, let's work on our piecewise function then. And you'll get some you'll get some experience graphing those step or greatest integer functions in your notes, in your homework. All right, so let's look at our domain. So this is the first one. We're going to start up at the top. And that one is going to go from -3 to 1. That's where that one goes. So that line, -2x plus 1, should be in that interval right there. Okay, so what I like to do is I like to get the point at the beginning of the interval. So I would do, we're going to do -3 first. So -2 times -3 plus 1. So at -3, we're at 7. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 is about right here. And it's okay to go off the graph. It's not always going to be perfect. Just kind of estimate where the 7 would be. I'm thinking it looks about right there. Then what I would do is I would put the ending one in. So -2 times 1 plus 1. Let's see, that's -2 plus that's -1. So at 1, I'm at -1, and that's going to be an open circle because it's less than 1, not less than or equal to 1. Now, since that's just the equation of a line, and I have 2 points on the line, what I would like to do is just use a ruler and connect the 2 points. If you want to put more, if you want to calculate more points between there, you certainly can. That'd be perfectly fine. I kind of want to stop and use the ruler. Okay, so there's that piece from -3 to 1. Okay, so the next piece is when x equals 1, and that's just one little spot at 1. I mean, there's no, there's no interval, it's just 1. And when x is 1, y is 2. So that's just a point. Okay, we can do that. The last piece is when x is larger than 1, so we're going to go start at 1 and we're going to get bigger. And that's the parabola x squared. So what I would like to do is start at 1, so 1 squared is 1. So 1, 1, and that's a circle because it's not or equal to. Then I would do a 2, 2 squared is 4. So 1, 2, 1, 2, 3, 4. And it's just going to keep going up. All right, so how's our graph? How are we doing? So let's look at what they want us to find. Part A, they want us to find f of -2. Well, we can look on the graph, -2. It looks like, I can't tell, -2, because my graph isn't perfect. I'm not really sure what that is. So what I'm going to have to do is calculate it using the graph, so the function. So f of -2 is going to be -2 times -2 plus 1, which is 4 plus 1, or 5. See, my graph is a little bit off. It should be crossing at 5. F of 1, so f of 1, oh, well, that's just 2. And f of 2, let's see, somewhere, f of 2 we found was 4. And if I couldn't read it off the graph, I would just put the 2 in here and get 2 squared, or 4. Okay, so let's look at domain. Domain is all of the x values. Now, our x values actually start at -3. Yes, ma'am. Are you good?
Oh, sorry.
Oh, no. Which is perfect. Okay, so x values start at -3. We don't have anything before -3. I mean, there's nothing over there, because it starts at -3 and then goes to 1. The first piece starts at -3. But we keep going all the way to infinity. I mean, there's a lot of x values after -3, but none before -3. Okay, intercepts. So intercepts are both x and y intercepts. So let's circle them on the graph. So that is an x-intercept and that is a y-intercept. And they both actually happen in the first piece. That's where both of those intercepts are, in the first piece. It doesn't always have to be like that. So if we want to find the x-intercept, this is just review from last year. The x-intercept, we would want to make y equal to 0. So 0 equals -2x plus 1. So 2x is 1, or x is 1/2. So my x-intercept is 1/2, 0. And that's what that little circled x-intercept would be. That's my x-intercept. Okay. For a y-intercept, what we would do is we would make x equal to 0. All right, so -2 times 0, what is it, -2x plus 1. -2 times 0 plus 1, which is 1. So 0, 1 would be our y-intercept, which I circled on the graph. The last thing they want us to do is to find the range. The range is all of the y values. So we need to start with the very lowest y value. The very lowest y value I can see on the graph is -1, but it's an open point, so it's not equal to, so I have to put a parenthesis. Now, this area right here, so let's look at this. See the area right between those two holes? That's concerning. That is concerning. I don't have any y's right there. But if I look to the left, I see I have those y's right there. So I'm okay. It's all right that those y's aren't there. Basically, I can use these y's in their place. So I don't have to take out a y value of 0 because I have a y value of 0. So my range, actually, it's okay. I can go past that. Now, the y values stop here, right over here where this little point is. The y values stop there, but on this side, they never stop. They go forever and ever. So I actually get to go all the way to infinity. So the range was a little weird to do, but what we need to think about is that y value included in the graph or not? If I asked you if the y value is 10 is included in the graph, you'd have to look and say, well, yeah, this piece is going to keep going up forever, so yeah, it's going to pass through a y value of 10, so that would be fine. Okay.